So here I would like to talk about a brief introduction into AI ML. By the way, how many of you do really understand AI ML? There are a lot of people here, so that makes my job much easier. Then we'll move on to the motivation for harnessing the power of AI and ML. I'll briefly talk about what we are doing with AI. I know we do a lot of things. I just wanted to give you a quick glimpse into what are the different things we are doing with AI at our organization. And then I'll jump on to AI used in the controls application. And then I'll conclude this with two industry use cases with formation flying as well as eVTOL vertical landing. So what is machine learning? So, basically we start with artificial learning as a broad canvas, wherein we could put many different kinds of computer learning systems in this bracket, which mimics the behavior of human intelligence. Now, the important difference between the typical programming versus artificial learning is the part where it is learning. In the program that we are writing so far, every instruction is explicitly given to the computer, whereas in case of artificial intelligence, we are expecting the machines to learn from the data that we provide to it. So of course, we started with artificial learning as a broader canvas. The machine learning is a subset of artificial learning, where machines learn from data. And within the machine learning, we have different subsets like deep learning and so on. And when it comes to machine learning, you have different classification, different kinds of machine learning there. So you have unsupervised learning, wherein you feed the data to the computer and let it identify the pattern or the characteristics of the data and then make the clustering around the data. So typically used to identify certain patterns in the data and then group it together. And then you have a supervised learning. The supervised learning is where you provide the data with label. And so you're saying, for example, if you're giving the image to the AI ML, you're going to label that image and say what that image is all about. It's a cat or it's a dog and so on. So you feed a series of such image to the machine, let the machine understand how to identify the cat versus a dog, so that after the training is done, when you provide a new image that the machine hasn't seen so far, it still is going to be able to make its judgment and say, okay, this one is cat or this one is dog. So that's your supervised learning. And then you have another category of deep learning where you have the deep reinstatement learning. Now, in this case, you have a deep learning agent that interacts with the environment and it learns what is its goal. In the environment, it interacts with, and whenever it does achieve its goal, it gets the rewards. So it understands or it reinforces the learning so that it gets better at its job. So that's about deep reinforcement learning. So these are the different flavors of AI ML. But of course, not only, there are so many other variants that are available. This is what we primarily are interested in this discussion. Now, with the brief background to AI ML, let's quickly look into the motivation. So why should we really look into AI ML? And again, once again, referring back to the question from the audience, so we already are motivated enough to look at AI and ML, and we are experiencing this everywhere. So it could be something to do with the image detection. It could be something to do with the audio voice detection. You have text-to-speech conversion that's automatically working. Could be on the weather prediction, could be on the medical application like cancer detection, tumor detection. And it can be used to enhance the cybersecurity. User preference analysis, for example, something like if you're going into the websites like Amazon, for example, if you have browsed certain items from the catalog, it can understand what is your interest. And it can come back with the prompt saying that you might be interested in this item as well, right? You buy a book, it says you might be interested in a couple of other books which are related. So it kind of automatically learns with what you do and proposes you what you could be interested in further. The same thing happens in YouTube, same thing happens in Netflix, so you have experienced it. And it can be used for the language translation, education, finance, and even trading. So there seems to be a couple of AI models that come up with the prompt or suggestion that which stock you could pick. And I believe there are certain AI models that are already working, and some of our friends are already using it and making profits. Now, I don't have enough money to invest in the stock market, so I'm waiting. So I'm waiting for somebody to come up with the AI model that tells me which lottery I should buy. So among the audience, if you are experts, I would like to talk to you next. Now, next thing, AI ML is driving transformation in mobility. So you already know ADAS and autonomous systems. You might already be driving some cars which has these autonomous capabilities. And then AI also has a lot of capabilities to help us in terms of, let's say, the natural disaster management. So it can help us identify people that are in need of help and get the help reaching up to them. It can help us in reducing the cost and risk in management of various activities that we do. Could be crowd control, could be law and order enforcement, and so on. And of course, it can help us improve the overall security of security. So with that motivation, let's quickly look into what we are doing at Ansys about AI ML. So we primarily have 5 pillars of innovation. We focus on numerical analysis, high performance computing, artificial intelligence and machine learning, cloud experience, as well as digital engineering. So these are the 5 pillars of innovation that we have identified, and we have a lot of R&D going on all of these topics. And today, of course, our focus is primarily around artificial intelligence and machine learning and what we could do with these advanced technologies. Just for your idea, what we are doing internally with AI ML, like these are the 3 main activities. Maybe Ansys GPT is going to be the first one that's quite easy for me to explain. So probably everyone here is familiar with ChatGPT. So you go to the prompt, type your question, so you get an answer. As simple as that. Ansys GPT is very similar. So it's our version of GPT, which has been trained about Ansys products. So we feed all the user manuals, the documentations, the internal articles, variety of literatures into this engine. And as a customer, you can ask a question here. What can I do with Ansys XYZ product? And you're most likely to get a good answer from this engine because it can sift through hundreds and thousands of pages of documentation and specifically come to you with the precise answer that you're looking for. That's the first thing that we are doing. The second thing we are doing is with Ansys Sim AI. It's basically an artificial or the machine learning agent that learns from your existing simulation. For example, you're coming up with a new product, maybe new aircraft or maybe new vehicle, and you quickly want to understand the aerodynamic performance of that particular machine. Now, this is an evolution over your previous designs, wherein you already have the model and you have done the simulation. So you can train this model with the existing information, and then you can ask your questions about the new model that you currently are designing. So typically, to run through the simulation, it's usually very time consuming, but with this one, it could be very fast. Could be minutes or even down to seconds. Now, of course, this is your first iteration towards simulation. The moment you get an understanding, you pick one of the iterations and then go for the detailed study, detailed simulation at a later point. The third one is AI Plus, which is basically specific AI ML based capabilities built into individual products that will enhance the user experience, which wasn't possible in the past. So that's basically what we do with the 3 different categories of AI adoption. And this is applicable across the product line. So we have this capability on Ansys fluids, Ansys structures, electronics, as well as optics. However, we are here mainly from the embedded system, from the safety and mission critical system. So what precisely are we doing in this area? To talk to you about that, let's get in here. Typically, when it comes to the safety and mission critical system, we are quite apprehensive about using something which we don't fully understand. And AI and ML, we know there is enormous potential, but at the same time, we look at it with a great caution. We don't know how we could make use of these things in the safety and mission critical technologies. Is it the same overall? Everyone in the globe is doing the same thing? There are people that are looking at it with a lot more optimism. And of course, all of us here are looking at it from the same perspective. We are very optimistic. From ESSS perspective, they have started work on this topic for over 4 years now. The first iteration of their guidance came in 2020, and now there is a second iteration. There are 2 more technical guidance that was released. And recently, FAA also said they're going to come up with their roadmap for AI, ML deployment in safety and mission critical systems. And what this document says is AI, and more specifically the ML field of the AI, is bringing an enormous potential for developing applications that would not have been possible with the current methodologies. And this document also identifies 3 important classifications where you could progressively adopt AI, ML into the kind of applications we develop. So the first one is level A. And again, each level is split into 2 parts, level 1A, 1B, similarly for level 2 and 3. So for level 1A, it is primarily about human augmentation. So human is completely in charge. You can use AI to bring in certain extra insights of the system to the person, so he can decide to do whatever he wants. In 1B, we have a little extension to that, human cognitive assistance in decision making and taking the actions. In level 2, we have AI supporting human with what's called as human AI teaming. So we distinguish this with the 2 different parts. One is the cooperation, the other one is collaboration. So the cooperation part is 2A, where the AI is acting like your subordinate. So you're going to ask the AI for whatever particular activity you need help on, and the AI will execute that activity and get you back the result. In case of collaboration, you are going to share the context. The machine has the access into what you're doing, and it knows what you're doing, and it can automatically come back to you and saying that, okay, look, I have a better proposal. Can you do this instead? So this is the distinction between 2A and 2B. And at level 3, the AI-based system performs decisions and actions. However, the human has the overriding capacity. So human is still the master, but you give a little more control to the AI so that it can take actions. And from level 3B, complete control over to AI. So these are the progressive steps in which EASA visualizes the adoption of AI and ML. However, the technology is still rapidly progressing, and most of what we are talking about can or may change depending on how the technology evolves itself. Now, given that we have a serious motivation to use AI and ML in our everyday life, let's quickly look into how could we apply this into the control systems. So the first thing is our handcrafted control applications, where the control strategy is pretty much well-defined. So you have a system, you have a controller, and you have a measured value, and you have a target. Then there's a feedback going on in here. So typical control system that we are pretty well used to. And for this kind of control systems, all the control strategies are very well defined in advance, and we have a clear set of requirements. So this fits very well into this kind of application. However, when it comes to the case where we are talking about advanced flying formation, or when we are talking about dynamic environments or unpredictable scenarios, the current control strategies may not really fit very well. Now, this is where we see the potential for bringing in AI, ML into it. So we spoke about deep reinforcement learning before. So we can bring in the deep reinforcement learning agent here, which interacts with its environment and automatically comes up with its decision to take care of these scenarios that we talk about. So when there is an unpredictable scenario, the machine already has in its learning, it knows what to do, so it takes the action automatically, which is best suited given that scenario. So this would be quite suitable for the kind of environments where we cannot really visualize all different scenarios that would unfold. For example, the scenario something like unmanned air vehicle flying without a pilot. Or maybe the scenarios where you are on a reconnaissance mission, there is no pilot on the aircraft, so it's completely up to the aircraft. So could be a formation flying. So there are many use cases where you have the potential to deploy AI ML. Now coming to the handcrafted control application, we do have a best of the tools, process, development, testing methodologies, certification techniques, everything is pretty well laid out. Now one of those approach is to a solution that starts with, let's say, a requirement. So you have all the requirements for your control application captured here with any of the tools, could be DOS, DOS-NG, CodeBeamer, and so on. And then you bring in those requirements and you create your overall system architecture. And as you are creating the system architecture, we would also want to look at this architecture from the safety and security perspective. We want to make sure that this architecture fits well because, like Nicola was talking about before, these attributes like safety, security, etc., are not bolt-on. So you have to design them right from the beginning. So you can connect it with another solution called Medini, which allows you to perform safety and security analysis. Once you refine these things, then we get down to the actual control development with Skate Suite, and then the HMI development with Skate Display. Then we move on to the testing part of it. We do the model simulation and we do the testing. So that would be the requirement-based testing, model coverage analysis. And of course, we also provide automatic translation of test scenarios that is integrated with LDRA tool suite. So you will be able to straight away bring it into LDRA, run it on the target as well. So you have the complete testing flow automated through this tool chain. Then with the click of a button, you generate implementation, you get the C code, and the C code is independent of the target platform, independent of the operating system, which means this entire algorithm or the control strategy that you developed can be deployed on the different kind of hardware, different kind of operating system that you might plan to use. Now, and this whole flow has been established and proven in use over a long period of time. So this entire process of design, development, implementation, verification is compliant to the industry standards, complies with DO 178C all the way up to DAL-A. And then there are multiple programs around the globe that have used this approach and successfully certified their products, and they're actually in deployment at this moment. Now, taking this discussion forward into the AI world, so what do we do here? How do we bring the artificial intelligence into the control world? Now, for those of you that already are familiar with AI ML environment, you know that most of the capabilities for you to design and develop and test the AI capabilities are based on Python environment. So we wouldn't want you to switch over from there into SCADE right at the beginning. So you still are going to be in your Python environment. You decide which neural network you're going to choose here, and then you train this neural network with the data that is relevant for the mission that you're designing. And once you train this, now you have a model that is trained. So when you say a model that is trained, you already have the biases, you have the weights and everything that is computed by the system. It's a model now in a good shape to be translated. And that's when we bring in SCADE. We provide you an importer which takes this Python model, which is primarily built on TensorFlow, and we support Keras interface that will automatically take your existing tested AI model into SCADE environment. Now here, you will get a SCADE project, and you will have everything coming from AI environment replicated within the SCADE environment. Now, what do we provide in the SCADE environment? We provide you a certifiable, small footprint, efficient code generation capability. So you get a C code here, and this C code can then be taken forward into your actual deployment, like the way how I have described in the previous slide. To look into this a little more deeply, so you have different neural network layers that already are supported in SCADE. Like for example, you have dense, CNN, pooling, RNN, so different kind of layers already supported. And you have different activation functions that are already built in, like sigmoid, softmax, ReLU, and so on. And it allows you to implement the different classical neural network designs. So we provide you a library that supports all of these capabilities. And on top of it, we want to make sure that the interface to the AI world remains same. So we have followed this entire integration, keeping in mind the Keras framework. So the documentation is completely in line with Keras framework, so it's nothing new to you. And once you do that, then you once again can go back to the Python environment, and you can reintegrate this back in the Python environment. So you have the C code, it's going to be wrapped around with Python, and then plug it back into your original Python environment. You can continue to validate this neural network that you have built. And once you're happy, go ahead, deploy this onto your actual system. So you have a mechanism where a small footprint, efficient C code that can go down all the way into your target. Now, so far, we looked into the entire possibility of creating the AI model in the Python environment, which you know already. Then we spoke about importing this into SCADA environment and automatically generating deterministic low footprint C code. And of course, the tool also has complete support for conventional testing, the requirement-based testing, model coverage analysis, and testing with the help of LDRA. However, there are a couple of things that we need to keep in mind here. The thing is, AI's operational explainability to support human AI teaming is something we still need to work on. For example, when I say AI human teaming, it's like the pair programming. So I have somebody sitting next to me, like in case of an aircraft, you have the pilot and you have a co-pilot. Each one has their own responsibility. If co-pilot is going to make a suggestion, he's going to justify his suggestion with his rationale. He says we should fly down to flight level 260, let's say. Okay, why? So that person will explain it to me because of so and so reason. You're stepping out of the home this morning, somebody says, take an umbrella. Why? It's probably going to rain this afternoon. I saw the prediction. No, it's a different case that if it is going to rain, nobody comes out of the house. But what's important here is that someone gives you not only the proposal, but they'll also explain why they made that decision. So it's important for us to understand the rationale behind a decision to build confidence to trust this AI mechanism. AI assurance in the context of programming versus learning. So we once again spoke about the difference between programming versus learning. So in case of programming, we have precisely given every single instruction to the computer, so we know what's going to happen. But learning is a kind of black box. We still do not fully understand how AI makes its decision. So that area needs a little more elaboration. Conventional testing may not provide enough confidence to deploy AI in critical systems. So that's the general opinion about the deployment of AI. However, there are a lot of discussions, a lot of technological developments, improvements are happening around this topic as we speak. So this is only a matter of time until we arrive at a situation where we are confident enough to deploy AI, again, progressively in the different ways that we discussed before. And there is also Part 2 certification. And this Part 2 certification may require some additional consideration because AI is completely different than our traditional approach to programming. Now, something that's very important here is, this is just a small piece of adopting AI into our environment, but there is a much bigger scope where AI can play a role in our environments, in our applications. So I want to explain these with two case stories. The first one is autonomous flying, formation flying of F-16 aircraft with AI assistance. Now, before I go into the details of what we are talking, let me just quickly play a video to give you an idea of what this exercise is all about. So here you see, it's a combination of two aircrafts. One is a lead aircraft, which is manually piloted. And this aircraft is followed by an ego aircraft, which is automated. There is a perception software on board, there is a neural network on board, and it is detecting the lead vehicle and maintaining a constant distance and following all the maneuvers of your lead vehicle. So it kind of does this job. So a series of 90-degree turns as part of the scenario execution, the lead pilot does, and your ego vehicle follows it faithfully. Now, this is what we want to do in this part of the exercise. Let's look into step-by-step example in terms of how are we going to look into this. The very first thing that we want to get started off is by defining the intended function and the key performance indicator for this entire mission. So it is to demonstrate the formation flying with two fixed wing aircrafts, executing a series of sharp turns. That's my intended functionality. And the functionality that I need to develop here includes all the flight control logic or the engine control logic for the lead vehicle, and then the AI-based perception software-based camera sensors for the ego aircraft, which precisely calculates the position and the orientation of the lead vehicle. Then AI-based automated aircraft stick agent to automatically control the instructions from the AI environment. So the key performance indicator is that it should manage this within a distance between 250 to 500 feet. Now, how are we going to get started with this? So we first define what's called as concept operations or ConOps, where we are going to create the overall mission of how this is going to look like. So we have the top level use case for the lead vehicle, then what the pilot would do in the lead vehicle, then the top level view of our ego vehicle, and what the AI enabled pilot would do here in the ego vehicle. And of course, there is a backup pilot in case if needed. Then we will move on to identify what would be the AI ML workflow, because that's the core of this entire exercise. Of course, we get started, so you have the detailed description about what are the different activities that needs to be carried out here. So the very first thing is we are going to define the top level system architecture for this whole function, and then we define what are the requirements for ML algorithm. How are we going to design this ML? What are the performance boundary of this ML? And what are the required or the expected behavior of this ML? Then we come here to define the overall system architecture. So this is a very important point again. So here we provide a complete framework for developing the architecture of the system. So we comply with SysML 2.0, which is the latest standard that's coming out from INCOSE. And this allows us to create the overall architecture of this kind of complex mission. So you create your architecture, you identify the important functional blocks of the system, you connect them in the sequence or the logical way in which they must be connected to realize this complex behavior. And then we move on to provide the ODDs and scenarios. So the ODD and scenario is basically the operational design domain. Now, talking about vehicles is probably much easier to explain. So when I want an automated vehicle, autonomous vehicle, I would want the vehicle to take over right from my parking lot or my garage all the way to my office. Now, however, you know that currently there is no such capability to make that happen. What we can do is a limited subset of this entire scenario, which is if you're driving your car under certain condition, like probably you're driving it on a highway, the lane marking is pretty visible, the weather condition is good, the speed is less than 80 kilometers, let's say. So if you are in that condition, then I am able to bring in the AI capabilities in here. So that's what we call here ODD. So operational design domain. It's a restricted environment of your overall design domain wherein the autonomous functionalities can be executed because there are a lot of limitation in the system that we are developing. And once we define the ODD, then we define the various scenarios that needs to be executed to give me the confidence that the system that I'm developing complies with the requirements of this ODD. And to do that, I need to run this with the different environmental conditions as well. So here, you can imagine that's not going to be the daylight scenario all the time. It could be early in the morning, or it could be late in the evening, or it could be cloudy environment, and so on. So I want to make sure the system that I'm developing is robust enough across the different environmental conditions. I also need to define at what altitude this mission is possible, because the moment you get into the clouds, the camera cannot see that aircraft anymore. So that's a limitation of my system. So how do I address that? So if I want to extend the ODD, I need to come up with the next technology to address this kind of limitations. And this is where we come into the model-based safety, security, and SOTIF analysis. First, from the safety perspective, you need to comply with the ARP standards or DO standards. And then there are separate standards for the security. And something that's also important here is complying with the SOTIF requirement. Now, when we are using these autonomous systems based on AI and ML, so we need to define the limitations of the sensors as well as the weakness of our perception environment. We have the camera, and if camera fails, if there is a malfunction in the camera, what should happen? That is primarily dealt by the functional safety part of the story. But despite having a fully functional camera, your mission may not still be successful, because if there is a direct sunlight hitting the camera, that will push the camera into saturation. For a couple of milliseconds, you will not have any image at all. What do you do in that situation? That's addressed by the SOTIF. So you have to systematically understand the weakness of the system, limitations of the system, and try to build the counter designs and counter arguments to ensure that it fits the ODD constraints that we have. And to do that here, we come up with the scenario-based evaluation approach, where we create the scenario and we identify which scenarios are important. So for us, what's most important is to have a set of scenarios that are completely representative of the ODD that we have chosen, which are robust, which are sensitive, so that I can completely cover the design domain I have in mind. And then we practically go and create this scenario. So we have solutions using which you will be able to create such scenarios, and then we can create synthetic images of this entire environment. For example, to train the AI/ML, you need a lot of data. Where are you going to get this data from? So practically, it is not possible for you to collect this data by flying through hundreds and thousands of miles of your ESSS. That's not feasible. So we have the environment where you can virtually create the images, which can be used to train your AI, that makes the overall mission much more faster and less expensive. Now, once we do all of this is when we actually get down to this mission, like the video that you have seen before. So we will be able to realize something like this. So this is a demo. So if you have some ideas like this, it is possible with a set of tool chains and the capabilities that we have that incorporates AI and ML into the overall workflow. The second case that I want to talk very quickly is a vertical landing of eVTOL use case. Now, this is something that is coming up quite rapidly all around us. So you see there are a lot of discussion going on in terms of air taxis. So the small set of vehicle, like 4 or 6 people can fly very quickly. Maybe if you want to fly from here to the airport, well, someday in the future this might happen. So how about realizing such use cases? So here you see the complete architecture of this use case. And I quickly want to run through the demonstration here. So you have the complete view of the system. For example, you have the perception software here, which is based on YOLO. And then you have the vehicle controller that was built into SCADE, vehicle dynamic model that's coming from the Modelica, the open source libraries, and then the complete integration platform is provided within SDK, the scenarios plus the integration platform. So here we have integrated the YOLO perception software with our digital twin environment, wherein you will be able to look at the image through the camera sensor and then identify whether this is the right image for me to land onto. And then we have the vehicle dynamics that is completely capturing the octocopter. And here you have the details about the various controls that are going into this physical machine. And then we have the vehicle behavior model that is done with the Modelica. So that provides me the feedback about controlling the vehicle. And then we have the scenarios that are brought in here into the SDK, which tells me precisely within the 3D dimension where I am at the moment and where I should move next to land in that particular spot. And when we run this simulation, you see that on the top left, you have the image of the vertiport. It's a picture or the image, or it's called vertiport, where your vertical takeoff and landing machine would land into. And on the right-hand side, you have this UAV, which is actually scanning around to find the spot for the landing. And what you see below here is the image perceived by the camera and understood by the perception software. So you see the bounding box here with the small number here, which indicates the confidence of your perception software that this is the correct landing spot. And once you are done with this, so you see that the aircraft is now homing onto this location. Finally, it is landing at that spot. And then you can see various performance parameters as we are running through the simulation. So if you need to optimize, tune, or rework on any of this, you have the possibility to do so. So that's pretty much I quickly wanted to talk about. So with that, we discussed about AI ML as a key enabler for autonomous functions, including the safety mission critical systems. And AI ML usage is spread across the system development, starting at the digital engineering, model-based system engineering. These are the enabling technologies to help us effectively adopt AI and ML. Of course, from our side as a tool provider, we continue to work with the different industries, domain-specific methodologies, like in case of autonomous vehicle or in autonomy in case of aerospace applications. And something that's very interesting and important is that we work with the complete industry ecosystem. So we want to make sure to percolate this idea to be present in the industry, to be understood and deployed in the industry. We work with authorities, we work with manufacturers, we work with suppliers, tool vendors, etc., to move forward the complete ecosystem and facilitate the adoption of these latest technologies in the industry. Now, as a mission, to support you, we have tied up with Incose. So if you are members to Incose, you have a chance to use any of our solution that's listed here for free. And of course, it is primarily for your personal use. So for you to understand how to make use of these tools, and you can create demos, you can use it for academic purposes and so on. So we support the industry by providing them all of these capabilities free of cost. So that's basically what I wanted to talk to you about. Thank you very much.